Linear regression works great when the data follows a straight line relationship. But what if the pattern bends? A single line can't capture curves. It underfits no matter how you try to tilt it. So, instead of changing the model, we change the input. We add nonlinear terms like x square, allowing the model to learn curvature while still staying linear in its parameters. That's the core idea behind polynomial regression. Now that we understand the need, let's build polynomial regression from scratch, mathematically and in code. Welcome to Decoding Complexities. I'm Pradeep. Imagine a dataset where students who study very little score low. Students who study moderately score high. But students who study excessively start burning out and score lower again. If we plot that, the points form a curve. A straight line cannot bend towards the pattern. It will always underfit. To allow bending, we create new features. If the original input is x, we generate x square, x cube, and so on. Each new power adds curvature. And importantly, the model is still linear in the parameters, meaning the math stays solvable with the same tools we used for linear regression. Polynomial regression is just a linear regression on an expanded feature space. Instead of modeling y equals w0 plus w1x, we model y equals w0 plus w1x plus w2x square. We can rewrite this in the matrix form as y equals x multiplied with the weight vector. And just like before, we solve for weight matrix using the normal equation. Same equation but a richer feature matrix. This is why polynomial regression is so powerful. The complexity is in the features, not the optimizer. Let's switch to Python. We start by importing NumPy for math, matplotlib to visualize the model, and Scikit-Learn strain test split to handle data splitting. These are the same 100 students we used earlier for our linear regression. This dataset has a natural curvature, perfect for polynomial regression. When we plot the points, we can see the pattern bending. A straight regression line would cut through the cloud but completely miss the structure. To make sure our model generalizes rather than memorizes, we use the train test split. We keep 75% of the data for training and the remaining 25% of the data for testing. The navy blue points are the examples our model is allowed to see. The red points are the secret test data. Now comes the critical step. We transform our input into polynomial features. This step is the entire heart of polynomial regression. We are giving the model the ability to learn curvature without introducing nonlinear parameters. Just like in linear regression, we compute the weight vector by calculating the dot product of x transpose x inverse with the x transpose y. This gives us the intercept, the slope, and the curvature term. Everything here is pure linear algebra. Our model has now learned the parabola that best fits the blue training points. Next, we use our learned parameters to generate predictions for both the training and test sets so that we can evaluate how well the model generalizes. The training error and test error are so close. That's the sign of a healthy model. Not too simple, not overfitting, capturing the true curvature in the pattern. Our polynomial regression curve bends naturally through the data cloud. Even for the red test points, which the model never saw, the predictions are so close. In production, we do not implement this from scratch every single time. If you would like to do the same thing using Scikit-Learn, we can use polynomial features to do the feature transformation. That is, to construct x square, x cube, and so on automatically. And then feed that into linear regression. Under the hood, Scikit-Learn is applying the exact same math we just derived manually. The key idea here is subtle but powerful. Polynomial regression is not a nonlinear model. It is a linear model applied to nonlinear features. All the complexity lives in the input transformation. The optimization stays simple. So, we started with a problem, a curved pattern that a straight line couldn't capture. We expanded the feature space using x square, solved the same linear equation as before, and discovered a model that bends naturally with the data. But what happens if adding more curvature makes the model unstable? Or if adding too many polynomial terms causes wild oscillations? That's where regularization comes in, and that's what we will decode in the next video. If this deep dive was valuable, check out the detailed companion blog post and the Google Colab notebook linked in the description to run this code for yourself. Hit that like button and subscribe as we continue to decode the complexities of machine learning. Thank you for watching, and I will see you in the next one.